Right now, every digital transaction you make, every file you save, and every application you run is supported by billions of calculations happening in remote server farms. It is a system of massive, invisible scale. The National Institute of Standards and Technology provides the formal definition for this system. They describe cloud computing as a model enabling ubiquitous, convenient, on-demand network access to a shared pool of configurable computing resources that can be rapidly provisioned with minimal management effort. Ask most people when the system was invented, and they'll point to the mid-2000s, treating the cloud as a sudden technological invention that appeared out of nowhere. But the hardware and system software in modern data centers didn't materialize overnight. The cloud is the result of 4 distinct evolutionary milestones in distributed systems architecture, spanning over 70 years of engineering. To understand how the cloud achieves seemingly infinite scale today, we have to look at how each previous era solved very specific physical and economic bottlenecks. This timeline charts distributed computing from 1950 to 2010. Phase 1, 1950s. Mainframes established centralized computing. Phase 2, clusters in the 1980s, interconnected smaller hardware. Phase 3, grids in the 1990s, utilized the global reach of the internet. Each of these 3 architectural leaps directly solved a problem of its time, providing a core structural requirement for the cloud systems we use today. The first leap was the mainframe. These were the earliest large-scale, highly reliable computers designed to process massive amounts of data. They established the concept of centralized resource sharing. Instead of a one-to-one relationship between a user and a machine, a single massive mainframe served multiple users and applications simultaneously, sharing CPU, memory, and storage efficiently. To make this work, engineers developed the single system image. Multiple processors operated internally, but to the end users accessing the system, it appeared as one unified, seamless environment. This centralization was ideal for bulk transaction processing. It became the backbone for industries requiring strict data integrity: banking, airline reservations, and enterprise government services. Because these systems were critical to national infrastructure, they were designed to be continuously available. If a component failed, an operator could swap it out without ever shutting down the active system. But mainframes faced a severe physical bottleneck. If a bank needed more computing power, they couldn't just plug in an add-on. They had to purchase an entirely new, physically massive, custom-built machine at an exorbitant capital cost. Mainframes proved that centralized resource management worked. But the extreme cost of custom hardware forced the industry to find a cheaper way to scale. In the 1980s, the solution emerged as cluster computing. Instead of building one giant custom machine, organizations began buying inexpensive, standard commodity computers, placing them in local networks and connecting them to act as a single system. This modular approach was cost-effective. You could achieve mainframe-level computational power simply by combining cheap, easily replaceable machines. This relied on parallel processing. Large tasks were divided among multiple nodes and executed simultaneously. It also established high availability. If one machine fails, the system doesn't stop. The network simply reroutes the task to remaining nodes. However, clusters were still physically constrained. They required a high-speed local area network, meaning all nodes had to exist in the same building, managed by a single organization. Clusters proved that scalable computing could be achieved with cheap commodity parts. The next step was breaking those nodes out of the local server room entirely. In the early 1990s, the rise of the commercial internet provided the infrastructure to break that physical boundary, resulting in grid computing. A grid connects geographically distributed computing resources across the globe, allowing them to be shared and utilized as a single virtual system. Unlike a cluster, which requires identical machines, a grid operates in a heterogeneous environment. It can link a Linux server in Tokyo with a Windows machine in New York, navigating different hardware and operating systems over the web. This allowed for utility-based access. For the first time, independent organizations, universities, and private companies could pool their distinct resources together and share computing power across institutional lines. This immense, decentralized processing power made grids suitable for data-intensive applications, like massive scientific research projects and complex environmental simulations. Grid computing proved that global, cross-organizational resource sharing over the internet was functional. It laid the philosophical groundwork for public utility networks. The subsequent development occurred in the 2000s. Driven by the demands of Web 2.0, the industry took the geographical reach of the grid and paired it with a critical new technology: virtualization. Virtualization is software abstracting physical resources into virtual machines. One physical server acts as multiple isolated virtual servers. By treating servers as software, systems achieve true elasticity. Resources are automatically provisioned, increasing or decreasing instantly according to workload demand. This enables vast resource pooling. Cloud providers build massive data centers, virtualize the hardware, and dynamically assign that computing power to millions of different users sharing the same physical infrastructure. This created a new service-oriented architecture. Data centers now deliver infrastructure, development platforms, and software applications directly over the internet as metered services. Virtualization decoupled computing power from physical hardware ownership, providing the structural basis for modern cloud environments. This decoupling changes how organizations approach the cost of their digital infrastructure. This diagram outlines the economic difference. On the left, traditional computing requires high capital expenditure. An organization has to buy their own servers up front based on their peak expected demand. For most of the year, that hardware sits there, underutilized. On the right, we have the cloud model. Because the resources are virtual and elastic, costs shift to a pay-per-use basis. Organizations rent infrastructure from a provider, scaling up when needed and paying strictly for what they consume. In this model, the burden of physical maintenance, hardware upgrades, and system availability is transferred away from the user and onto the cloud provider. Cloud computing replaces upfront capital investments with scalable, low-maintenance operating expenses. We refer to this end state as the utility computing model. Computing resources, processing power, storage, and networking are now provisioned exactly like municipal electricity or water. You turn a tap, consume what you need, and receive a bill at the end of the month based on usage. This accelerates development across the board. Software engineers no longer spend months ordering and configuring hardware. They request a virtual environment and focus immediately on their application's logic. Getting here took decades of iterative engineering. Mainframes centralized the process. Clusters made it modular and parallel. Grids connected it across the globe, and virtualization made it elastic. The cloud abstracts both hardware and economics, the result of a 70-year process that transformed computing from a physical constraint into an on-demand utility.